Video problem 56, changes of state. This is actually a pretty big problem, has a lot of ideas built into it. Let's just talk about the general concept here. It says determine the total amount of energy needed to raise the temperature of 15 grams of solid methanol from negative 120 degrees Celsius to a gas at 85 degrees Celsius. First of all, on your notes, there's a problem. The melting point should be negative 97.6. The boiling point should be 64.7. Had those switched, so sorry about that. So go ahead and make that change. All right, let's talk about what's going on. I'm going to draw an energy diagram over here. Okay, so it's going to be temperature on the y-axis. It's measured in degrees Celsius. And it's going to be basically energy added on the x-axis. Okay, so what's happening here is we're starting at negative 120 degrees Celsius. So there's negative 120 degrees Celsius. We're going to raise that temperature. That's a solid at that point. We're going to raise that to negative 97.6 degrees Celsius. So right here, we're going to call that negative 97.6, which is the melting point, and then it's going to melt. And that energy, like I said in the lecture video, that energy there is being used to weaken the intermolecular forces, sort of separate the molecules from each other, okay, from a solid to a liquid. And then we're going to increase the temperature to 64.7. All right, I don't really need the degrees Celsius there, to 64.7, and that is the boiling point. So at that point, again, temperature is not increasing, so we're not increasing our kinetic energy. What we're increasing is our potential energy. So all of the energy is being used to completely break the intermolecular forces. We're completely breaking the attraction that the molecules have for each other to turn it into a gas. And then at that point, we are going up to a final temperature of 85 degrees Celsius. So that's going to be as a gas. So we got a solid there, we got a liquid here, we have a gas there. Anywhere it's a plateau, we have equilibrium between the solid and the liquid. So in other words, the solid and the liquid exist. Here, at this point, the liquid and the gas exist. All right, let me label these, get some letters going here. All right, so we're going to call this line A, line B, line C, line D, and line E. All right, now for lines A, C, and E, the temperature is changing. So for lines A, C, and E, we can use Q is equal to M SH delta T, because what we're looking for is the total amount of energy, right? So whenever the temperature is changing, we can use Q equals MSH delta T, or Q equals MC delta T is what you'll see in AP, but yeah, SH and C are the same, okay, interchangeable. Now at points B and D, we don't have a temperature change, so we can't use Q equals MSH delta T. Notice that our specific heat capacity, our heat of fusion is given to us in moles here. Okay, so B and D we're gonna use this equation. Q is equal to N times delta H, where N is the number of moles. Okay. So we're gonna have two different types of equations, 5 different complete problems. Right, so let's go ahead and get started, and we'll look at a couple things that are going to come up here. Let's start with with line A. So line A, the temperature is changing, so I am going to use Q is equal to M SH delta T. But I noticed something while I was underlining over here. So here, this is the specific heat capacity of the solid, right? So line A is of the solid. Right? So I'm going to use the specific heat capacity of the solid, and it's 3.28, but look at the units. The units are a little bit different than what we normally see. The units are joules per mole Kelvin. So I can't use 15 grams. That means I need to convert that. Sorry about that. There was a very loud truck going by the window there. It's a nice day out, so I got the windows open. You don't care. All right, so we can't use grams here because my units here are moles. Units have to agree. So I'm going to have to change my grams to moles, which is going to change this. Now this is going to be Q is equal to N SH delta T, because my specific heat capacity is given to me in moles. Again, not something we normally see. All right. So now let's go ahead and convert that 15 grams to moles. That should be an easy process for you. We've got 15 grams of methanol, which happens to be CH3OH. I don't expect you to know that. Okay. The molar mass is 32 grams for every 1 mole. So 15 divided by 32, it's right at about 0.5, but let's get the actual value. And I get a value of 0.46875. And that's moles of CH3OH methanol. Okay. So when I plug that in over here, I'm looking for Q. We're going to call this Q sub A because this is line A. So it's going to be equal to 0.46875. I'm just going to write 469, but I'm going to use the whole number. Okay, that's moles. I'll show you the units for this first one here. The specific heat capacity is 3.28 joules per mole Kelvin. And then delta T is always final minus initial. So the final temperature is going to be negative 97.6 minus the initial temperature, which is negative 120. Okay, now it's in Kelvin, but a delta T in Celsius, so let me write this down here, a delta T in degrees Celsius is equal to a delta T in Kelvin. All right, so we can leave it in Celsius. We don't have to change that to Kelvin. All right, so what do we get? We got 0.469 times 3.28 times negative 92 or 97. It's a big difference. 0.6 minus negative 120, and I get a value of 34. Let's call it 46. All right, now let's look at units. Moles cancel out. Delta T Celsius, delta T Kelvin, same thing. So this is actually Kelvin. Kelvin cancels out, so we end up with the units of joules. All right, so Q sub A is 34.46 joules. All right, let's go on to B. All right, so point B is that plateau right there. All right, we said we're going to use this equation. So here's B, and this is going from solid to liquid, right? So I need, here, let's write down the equation. That's Q, that's going to be Q sub B is equal to N times delta H. Now, is this delta H fusion or vaporization? Melting is fusion. So this is delta H fusion, and it's 3.18 kilojoules per mole. So I already know what N is. N is going to be that 0.469 number again. Okay, that's moles. My delta H fusion is 3.18. And again, that's going to be kilojoules per mole. All right, so I'm just pretty simple. 0.46875 times 3.18, negative value of 1.491. I'm going to leave 4 sig figs because this isn't the end. I'm going to add all these up. All right, moles cancel out, and that's kilojoules. I should probably just keep it to 3 sig figs, but that's okay. So that's Q sub B. Notice that's kilojoules. This value up here is in joules, so we got to keep that in mind. Okay. Now I'm just going to do the rest, right? Because the rest are just like these, right? So let's go ahead and do C. Let's do C down here. Right? And C is the liquid, and C is where we're going from negative 97.6 to 64.7. All right. So we're going to use, the temperature's changing, we're going to use Q is equal to N SH delta T. That's that 0.469 number. All right. The SH now is different because it's the specific heat capacity of liquid. A solid, liquid, and gas are going to have different specific heat capacities. This one's 2.48. So that's 2.48. And that's joules per mole Kelvin. Again, that's a weird unit. We usually don't see it in joules per mole Kelvin. It's usually joules per gram. And then the delta T is what? Final, which is 64.7, minus initial, which is negative 97.6. So, all right. So let's calculate that out. That 46875 number, just going to go up and grab that, times 2.48 times the difference of 64.7 minus negative 97.6. So I get a value of 188.674, and that's Q sub C, we're going to call that 188.674, and that's in joules. Okay? So let's go on to D. Now D is a plateau again. So I'm going to use this value. Alright, so I'm going to put part D right here. And part D is going from liquid to gas. Okay, so it's going to be Q sub D is equal to N times delta H. This is going to be delta H vaporization. We know what that N is 0.46875, I think. Right? That's moles. My delta H vaporization is huge. 38.3 kilojoules per mole. Now remember, that's because we're totally breaking those intermolecular forces, where when we're melting this 3.18 value, we're only weakening the intermolecular forces. Okay, so big difference. So that's 38.3, and that's going to be kilojoules per mole. All right, so what do we get there? We get 0.46875 times 38.3, and I get a value of 17.95. So Q sub D is equal to 17.95. Moles cancel out. I end up with units of kilojoules. Again, that's kilojoules. And then finally, that E value, which is just a gas, right? So that's going to be Q is equal to N times SH delta T. So that's 0.46875. That's moles. Now we're using the specific heat capacity of the gas. So the specific heat capacity of the gas is right there. The smallest amount takes the least amount of energy to warm that up. So that's 1.06 joules per mole Kelvin. And then the delta T is final minus initial, so it's going to be 85 minus 64.7. Alright. So let's see what we get. 0.46875 times 1.06 times 85 minus 64.7. And I get a value of 10.09. That we're going to call that Q sub E. So Q sub E is equal to 10.09. And that's joules. So if I want the total energy, so the Q total, let's call it, I'm going to take Q sub A plus Q sub B plus Q sub C, Q sub D, Q sub E. I'm just going to add them all together. Okay? And so let's see what we get. We got Q sub A, which is 34.46 joules, plus Q sub B, we'll go ahead and make it in joules, 1,491 joules, plus Q sub C, which is right here, that's 188.674 joules. A lot of my sig figs are all over the place. I apologize for that. QD 17,950 joules. Whew, that's a biggie. And QE, which is 10.09 joules. All right. So when I add those all up, which I am assuming you can do easily as well, I get a value of my Q total is equal to 19,674, let's just call it like that, joules. So that's how much energy it takes to heat up, melt, heat up, vaporize, and heat up methanol. Now let me make one point here. Look at this huge amount of energy it takes to go from liquid to gas. Okay, now if we're talking about water, okay, so this point on water is 100 degrees Celsius liquid, boiling water, to 100 degrees Celsius gas, vapor water. Now 100 degrees Celsius liquid, boiling water, will scald you. It'll give you a pretty good scald. All right, it'll hurt, but you're going to be okay. 100 degrees Celsius gas will burn you. You will not be okay. That's a very nasty burn. Why? What's the difference? It's the amount of energy it takes to go from the liquid to the gas. That's the difference. There's a ton of energy that this gas has, since it is all separated, that this liquid does not have. It's a little extra bonus for you.